Hi, my name is Escher, and this is Physics 2212, Lab 4, Permanent Dipole Magnets. So the purpose of this lab was to measure and predict the distance dependence of the magnetic field using experimental values and the Biot-Savart law, and then compare the results of the two. A brief glimpse into the findings was that we found that N equals negative 3.0085, and that the magnetic dipole moment mu is 3.684. The fundamental principles used in this lab is the Biot-Savart law, which essentially relates a charge or current to the magnetic field that it creates, the magnetic field of a dipole, which describes the magnetic field of a bar magnet, and the distance decay formula, which describes how distance factors into the magnetic field of a bar magnet, the magnitude of that magnetic field. So the procedure for this first part of the experiment was to orient the phone and bar magnet perpendicular to the Earth's field. Then we would find the location of the magnometer chip inside the phone, and then measure the distance from the magnometer to the bar magnet at different strengths of that magnet. The system was the bar magnet, and the surroundings was everything else, the phone, the Earth, etc. So as you can see, for our part 1 data, on the left here is the table at which we recorded the values, found their average, and then plotted it on the graph to the right, where we see that as we increase in the distance, the magnetic field strengths fall off, or as the magnetic field strengths increase, the distance also decreases. To calculate the dipole moment of this bar magnet, we can use the values from the line of best fit calculated by Excel. The N value that we used is the slope value, and the y-intercept we use as the log of k, which then we could plug into the distance decay formula to then find mu. So for the second part of the experiment, we then measured the distance and the magnetic field when the magnometer was off the axis of the dipole magnet. This allowed us to see the once again the strength of the magnet based on the distance that the magnometer is away from it, as well as how the Earth affects the pull of that magnet. So then we made a computational model to again, once again, model that magnetic field that we are observing. So over on the right here, you can see the initial conditions. We plugged in what we found for mu, and then created a magnetic field function on the top left here, utilizing the Biot-Savart law to determine the magnetic field. And then obviously the arrows that represent each part of the dipole diagram, and then finally arrows at 45 degrees, and then the final computational model on the right here, where you can see that the arrows that are parallel with the dipole are facing to the right, and the arrows perpendicular are facing to the left. And we can see that the off-axis 45-degree arrow at the top right has gotten pulled by the Earth itself, and is why it's not facing the normal dipole pattern. And that's also the reason for the perpendicular arrows to be less than the parallel ones. Possible errors is that other devices could have skewed the magnometer readings. The location of the magnometer within the phone could have been incorrectly pinpointed, and Earth's magnetic north could have been incorrectly found, which would all affect the results of the magnometer. Finally, the discussion. So what if we hadn't oriented our experiment to compensate for magnetic north, and instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? Our results would have changed because the Earth's magnetic field would be factored into the magnetic field read by the magnometer, therefore interfering with the results, as we see with the arrows at 45 degrees and the perpendicular arrows. And what if we were to stick two identical magnets together end to end and run the experiment again? This would double the output of the magnetic field, therefore doubling our results, but the direction would stay the same.